Okay. So let's get started today. We are moving on to our second topic in design of databases, and that is normalization. If you'll remember from last time, basically, entity relationship modeling is a top-down approach, and normalization is a bottom-up approach. I find usually people use the entity relationship model in order to design a database, but sometimes when you're done, it still is useful to employ normalization to check your design. And as an example, I'm going to show you again the investment case design that we had last time. So in the investment firm design case, we saw that D said that each investor's holding of a stock contains information about the stock's ticker symbol, the stock's name, the number of shares owned by the investor, and the dividend per share. So you might very well end up designing something where you say holding, and you have something like a investor ID and a ticker, and you might have a dividend and the company name. And then elsewhere, you also have something called a relation called stock from stock gets purchased or sold. We record the stock's ticker symbol, transaction price, date, number of shares purchased. And so it's possible that there too in transaction, you would end up saying something like, whoops, that was holding investor. You might end up with a transaction or a purchase. And you might also have something like investor ID, advisor ID, ticker, dividend, company name, probably a price. So you end up with these two relations, but there's redundant data in them. So it's a natural thing to come up with based on the description of the investment firm case study, but it should look to you that this maybe isn't what we want. Okay? And it should occur to you that in some sense, the stock's ticker symbol probably determines the dividend and the company's name. And probably the converse, you probably also would have company name probably determines the dividend and the stock's ticker symbol. So we call this a functional dependency. Because the left-hand side uniquely determines the right-hand side. So it's a function. And when we have this kind of functional, I said div-n, shouldn't have a n in the dividend, but at any rate, when you have a functional dependency like that, it turns out that normalization gives us a way to decompose the relations, to pull this information in the functional dependency out of a relation and into a new relation. So we'll see that given that we can identify this as a functional dependency, we might actually end up with a new relation called stock that has ticker, dividend, and company name. And a functional dependency, in effect, gives us the primary key because the primary key uniquely identifies each tuple. Here, there's two possible primary keys for stock. What are they, based on what you see? What are the two potential primary keys for stock? Pardon? Ticker and company name. Very good. And which one should we use?
Ticker.
Ticker. Why?
It's
Let Phil.
be closer to being unique than company name.
Well, no, those, okay, so the functional dependency there is claiming that both of them uniquely determine it. So there's another reason though. So either of them can be the primary key. I'm claiming either of them uniquely determines a stock. Ticker is shorter, more compact. So generally we're aiming for the more compact key because it may end up as a foreign key in another relation. So it takes up less space. At any rate, normalization is going to give us a way to remove these functional dependencies, and then we would end up also removing from here, we would only keep the ticker in here, which is the determinant, and in here we would only keep the ticker. So the ticker would in effect become a foreign key that could then be used to join each of these two relations with the stock in order to get that information back. So normalization here, this process I showed you, gives you a hint of normalization. I'm going to walk through step by step the process of normalization, but I was just trying to motivate it that even when you're done with your ER diagrams and you've formed your relations from them, you may actually be duplicating data in the relations, and you'd like to have an algorithmic way to eliminate that duplicate information. So even if you don't use the normalization method as your primary method for designing a database, it's still very helpful for checking your design. So coming back here, so normalization is a technique that's going to allow us to decompose relations into groupings of logically related attributes based on something called functional dependencies, which is what I just showed you. Okay, and it's going to minimize the amount of redundancy in the database. And by minimizing the amount of redundancy, it's going to reduce the chances for introducing inconsistent data into the database. So essentially, normalization tries to ensure that the only duplicated information is keys, and that any other information is not duplicated. Even when we fix the chasm trap, remember when we fixed the chasm trap last Thursday, and it introduced a new branch number, and it was a redundancy, but that was still a foreign key. So normalization is basically trying to limit redundancy to foreign keys. Okay, so that's a useful thing to write down. So normalization may not always be successful, but it seeks to reduce the amount of elimination or redundancy to foreign keys only. And the foreign keys can be used to join relations together in order to retrieve any attribute information we need. Okay, so there's a number of what we call anomalies that are associated with data redundancy. They're basically characterized into three types: insertion anomalies, update anomalies, and delete anomalies. So if you just look at this relation, which is a combination of the staff and branch relation, so maybe when you're designing your ER diagram, you came up with this relation rather than with independent staff and branch relations, you can see that there's redundant data in this relation. So for example, the branch address may be duplicated multiple times. You see 163 Main Street, Glasgow is in there 3 times. And that can lead to some issues. Let's say that we move down the street to 105 Main Street, Glasgow. Then we need to remember to update all B address entries that are equal to 163 Main Street, Glasgow. And if we forget one of them, then we'll have inconsistency in our database. So we call that an update anomaly, because in updating the branch address, it's possible that we end up with some inconsistent data. But there are some other problems. Okay, let's say we want to insert a new tuple into this relation. To do that, before we do that, let's think about what is the primary key for this relation. Does anyone want to venture a guess as to which attribute or set of attributes uniquely determines each tuple? Staff number, very good. So the staff number uniquely determines each tuple. So let's say that we've built a new branch, but we haven't staffed it yet. We just built a new branch and we want to insert the branch number and the branch address into our relation. And it's the only place where we keep branch information, so it's the only place we're going to be allowed to store information to a branch into the staff branch. But it has no staff members. So if we want to insert the tuple for our new branch into this relation, we have to use nulls for the staff number, the staff name, the position, and the salary, because there's no staff member associated with this branch. Okay? That violates something about the relational model. What does it violate? The primary key can't be null. That's called entity integrity. It violates entity integrity. So that's called an insert anomaly. We're not actually able, while we can actually insert new staff into this relation, we can't insert new branches into this relation unless they have a staff member with them. So that's inconvenient. Okay? And then the final issue is what's called a delete anomaly. So let's say that we delete Mary Howe from this relation. Well, you notice something about Mary Howe that is different than any other employee. Very good, Jaja. She's the only one in branch 007. So if I delete the tuple associated with Mary Howe, I lose the information about branch 7. I no longer have information about its branch address or its branch number. So that's called a delete anomaly, where I potentially lose valuable information when I delete something from a relation. So these 3 types of anomalies are all obviously bad. And we want to be able to design our relations so that we avoid these three types of anomalies. So it should be clear that the staff branch relation is not a good one. It's poorly designed, and it could lead to problems in our database if it remains this way. And what we would like to do is decompose this relation into two or more subrelations that won't be subject to these three types of anomalies. Okay, and we will do that with functional dependencies. So the next few slides simply talk about what I just did, that an insert anomaly essentially occurs when I want to insert information about an entity into a relation, but in order to do that, I would have to insert a tuple with nulls for the primary key. And since I can't do that, I can't insert information about that entity. So that's an insertion anomaly. Then the update anomaly occurs when I have redundant information about some attribute, and when I update one tuple with that attribute, I may forget to update some other tuples that have the same attribute value. That will lead to inconsistencies. And then the delete anomaly is that if I delete information about some entity, then I delete, or if I delete a tuple, I may delete some information about that entity. So a second thing we're going to find is that typically it's bad for a relation to store information about more than one entity. The real problem with that staff branch relation is that it's storing information about both staff members and branches. But it's primarily storing information about staff. And we're also using it kind of in a secondary way to store information about branches. But that's what's really leading us into difficulty, is that we're using that relation to store information about more than one entity. So typically, we only want to store information about one entity in a relation. But it's not always that easy, because back here with holding and purchase, it wasn't necessarily obvious that we were storing information about more than one entity. In each case, for holding and purchase, we really were storing information about just one entity, the stock, but in that case, two different relations were storing the same information. So that's a different problem, but still a related problem of having redundant information. Okay, so the whole point with normalization is that we want to decompose relations into two or more what I would call subrelations. And when we do that, there's two properties we want to maintain. First of all, something called the lossless joint, which means that if the original relation contained some information, and then we decompose it into two subrelations, we should be able to, if needed, rejoin those two relations to form the original relation and not lose any information. So the lossless join property says we don't lose information when we perform this decomposition. And the dependency preservation property says that if there is some functional dependency between some set of attributes, so the ticker symbol determines the company name and the dividend, that functional dependency is preserved in one of the subrelations. It's not destroyed. So for every functional dependency that holds in the original relation, each functional dependency still holds in one of the subrelations. So those are the two things that it's looking for. And the way we preserve or enforce the lossless joint property is with foreign keys. And we also are going to preserve it because basically we're going to use functional dependencies to guide us in our decompositions. And the left side of the functional dependency is going to end up being the foreign key. Okay, so functional dependencies are huge in normalization, and you are familiar with them. It's just saying that if A and B are attributes and A uniquely determines B, then we say that B is functionally dependent on A. And instead of saying f of A equals B, we write it as an arrow. So we say A arrow B, meaning A determines B. Okay, so staff number determines position is a functional dependency, but position conversely does not uniquely determine a staff number. For example, we may have multiple managers, or we might have multiple sales agents. So just because the relationship goes in one direction doesn't mean it goes in the other direction. Okay, so we call the left-hand side the determinant. Just an easy way to refer to the group of attributes that make up the left-hand side of a function. And an important thing about functional dependencies is just because you have some data that seems to imply a functional dependency, you can't assume just based on that data that the functional dependency exists. So Dr. Planck has a name for leaping from example data to laws. What does he call it? He calls it proof by Cosmo. So in his younger days, I think his ex-wife or ex-girlfriend subscribed to Cosmopolitan magazine, and apparently Cosmopolitan magazine can make some pretty outrageous claims that aren't necessarily backed up by facts. They would just provide a few anecdotes and then say, well, based on these anecdotes, we can conclude. Well, it's the same thing here. You can't just say, well, I see these few examples, I therefore conclude, because the examples say that it's true. So as an example, if we just look back at the staff-branch relationship, we would tend to think, just looking at it, that the staff name uniquely determines the staff number because we don't see any duplicated staff names there. So if we just look at this example data, we say that one of the functional dependencies is staff name determines staff number. But you can't just look at this example data. Do we really believe in general that staff names will always be unique? No. Okay, we know that in the real world that there are some duplicate names out there. Okay, I don't think that there's a duplicate for Brad Vanderzanden, but I actually do know that my father, James Vanderzanden, is duplicated by a professor of chemistry somewhere. So even as unusual a name as Vanderzanden, my dad is still duplicated. So it's possible that we could hire an employee that has the same name as an existing employee. So just because we don't currently have an employee with a duplicate name doesn't mean it couldn't happen in the future. So we're not allowed Okay, so bottom line is if you say something is a functional dependency, it needs to exist and hold for all time, not just in your example data. So while it's true here that a staff number determines a staff name, it is not true that a staff name determines a staff number. Okay? Now, another thing we have to be careful about with functional dependencies is that we want them to be minimal. We want the determinant to be the minimum number of attributes that are required to uniquely determine the attributes on the right-hand side. Does someone remember from way back when there was a type of key that mimics this? There's a name for that key. Candidate key. Very good. Essentially, a determinant is a candidate key if it is, or a full functional, let me backtrack. The determinant in a full functional dependency is a candidate key. So let me write that down. Okay, so the determinant in a full functional dependency is a candidate key. So it is a minimal number of attributes that uniquely determines a set of attributes on the right-hand side. Okay, if we don't have that, it is called a partial dependence. Whoops, go ahead.
I'm confused like on the functional dependency. You say like a staff number is like manager and staff number. Well, you say it has to hold for all time, but what if somebody was promoted or demoted? Wouldn't that change their position and they'd keep the same staff number?
But the staff number would still uniquely, at that moment in time, it would uniquely determine their position. So you're right, at some point in time, I might give you a promotion. And it would change your position. But still, at that point in time, it would uniquely determine what your position was. You would be guaranteed that there would not be a second, let's say your employee number was S10. Okay, you would be guaranteed that there wouldn't be a second tuple in the database with S10 in a different position. Okay, so that's what it means. It means that given an attribute value like S10, there is a unique value for that attribute currently in the database. So it's not that you can't change the value, but that if you change the value, it's still unique for that particular determinant. Okay, so if something is not if there's too many attributes on the left-hand side, if it's not a minimal set of attributes, then we call the dependency a partial functional dependency. So it is true that the staff number and the staff member's name uniquely determines the branch at which the staff person works. But branch number is also functionally dependent on just staff number. So I could say staff number, okay? So if I just say staff number, does that work? Nope. Uh-oh. Did I freeze? Yes. No? Yes? Sorry, what I have is a new version of PowerPoint and it's clearly not always behaving quite the way I would want. Okay, so branch number uniquely depends on staff number. So we say that the determinant staff number staff name is actually a partial dependency because I could eliminate staff name and still have the functional dependency. So the full functional dependency is staff number determines branch number. The partial dependency has the extra attributes in it. Okay, so there's a review of the important characteristics of functional dependencies. A one-to-one relationship between the left-hand side and the right-hand side holds for all time And the determinant is the minimum number of necessary attributes. Okay? Then we also have what's called a transitive dependency. So we say if A determines B and B determines C, then C transitively depends on A. So A determines C in this case. Okay, so do we have an example? Yes. So we know that the staff number determines all those characteristics of a staff member on top. And we also know that a branch number essentially determines all the characteristics of a branch. So a staff number determines a branch number, and a branch number determines a branch address, and therefore there is a transitive dependency of branch number on staff number. Okay, so the fact that we have, the fact that staff number determines branch number, and branch number determines branch address means that staff number determines the branch address. So we call that a transitive dependency. And this is also something that we're going to seek to ensure doesn't, we're going to seek to move transitive dependencies to their own relations. So in this case, the fact that branch number determines branch address would suggest we would tend to move those two attributes to their own relation. Okay, so when you're doing normalization, typically you are trying to identify functional dependencies among the various attributes. So in this case, we have the staff branch relation, and we're going to make an assumption that the position an employee holds in the branch determines the staff's salary. So this is kind of arbitrary, but maybe we don't want to get a situation where two employees at the same branch have different salaries. Perhaps we think that would be divisive. So we decide that if one person gets a raise, all people with that position get a raise. So if we do that, we can probably set up this set of dependencies. So a staff number determines someone's name, position, salary, and branch. The branch number determines their branch address. Now there's some other ones there. Probably the branch address uniquely determines your branch number. Seems pretty reasonable. And I just told you that the branch number, that everyone at the same branch makes the same salary. So that's saying that the branch number and position determine a salary, and that the branch address and a position determine a salary. And you might say, so in this case, both staff number determines salary and the two pairs at the bottom uniquely determine salary. All of them are full functional dependencies. Okay? You might say, well, staff number is a fewer number of attributes. It's true, but staff number is not a part of the last two functional dependencies. I can't remove from the last two functional dependencies, I cannot remove an attribute and still uniquely determine salary. So these are the functional dependencies for the staff branch relation. So questions about that? Okay. So the functional dependencies are essentially the one type of integrity constraint that you want to enforce. Okay, they're not the only type, but they certainly are saying that essentially when you identify functional dependencies, you've identified some keys, and you want to ensure that the values on the right-hand side are unique for those functional dependencies. Okay? So we're also looking for candidate keys, which are keys that uniquely identify tuples, and we select one of those to be a primary key. So when we look at our functional dependencies, we're often looking to see if there's something that uniquely determines all the tuples. Well, back here, there's no functional dependency that uniquely determines all the attributes in our relation, just based on this. Okay, because staff number comes close, but it doesn't determine the branch address, based just on the functional dependencies you see there. Okay, so why can we still say that staff number is a primary key or a candidate key? What deduction, so to speak, allows us to make it a candidate key? Pardon? Well, it uniquely identifies the staff, but it doesn't uniquely identify every attribute. It doesn't, from there, there's no branch address. On the top line, you don't see branch address. Pardon?
Isn't that showing us we should have two relations?
No, all we're trying to do is find the primary key here. Okay, what I'm looking for is that there's a transitive dependency between staff number and branch address. I went through that not long, but I went through that conversation about the fact that staff number transitively determines branch address because of that second functional dependency. So sometimes I need to apply transitive dependencies as well, and when I do that, then I see that staff number uniquely determines all of the other attributes in the staff branch relation. So it may be that none of our functional dependencies by themselves gives us a primary key, but when we also bring transitive dependencies into play, we may be able to derive a primary key. Okay, so once we have our functional dependencies, what we want to do is start applying our normalization algorithm. So we first identify functional dependencies, then we start our normalization algorithm. And that's a series of steps that are going to decompose a single relation into some set of subrelations. And the first thing that we do, well, as normalization, we talk about degrees of normalization. So we start with first degree normal form, second degree normal form. BCNF is Boyce-Codd normal form. There's fifth normal form. People have come up with a whole bunch of normal forms, each of which is more restricted than the one before it. The ones that are most helpful are first, second, and third normal form, and that's as high as we're going to get in this course. The higher you get, the more esoteric you get, the less helpful it is, and in fact, you're sometimes not always, you're eliminating one kind of redundancy and introducing another kind in some of the higher normal forms. So we restrict ourselves to first, second, and third. So to get our initial set of relations, we simply create a table with our data. So we might use forms for that. Forms are a very handy thing. We might talk to employees, but we just come up with a set of initial tables. And one common thing to do is to create what's called the universal relation. So it is one relation that contains all the attributes for the DB. And then we break down the relation or decompose it using our normalization process. So one thing that's often done with normalization is we just start with one enormous relation. And in that we might list, so for a branch, we might have something like branch number and phone is two of the attributes. So we just start listing the information. Okay, and when we do that, we may decide that that branch number is a primary key, yet it has a repeating value. So phone is clearly, branch number does not uniquely determine phone. But we might decide that phone is a multivalued attribute. So while a branch may not uniquely identify a phone number, it may uniquely identify a set of phone numbers, meaning that if we have two branches, B1 and B2, each of them define a set of unique or non-overlapping phone numbers. So these phone numbers are different from these phone numbers. There's no overlap. The intersection for all sets is empty. Okay, so that's the definition of a multivalued attribute. It is uniquely determining the set of phone numbers for that branch. It's just that there's more than one value for that attribute. Okay, now we can't have that in the relational model. The relational model says we can't have more than one value for an attribute. And so, what we need to do in that case is to eliminate any multivalued attribute. And there's two ways to go about that. We can count up the cardinality of the largest set of multivalued attributes. For example, if a branch can have at most 3 phone numbers, we would create 3 columns for that attribute. Or we put the repeating data, the multivalued attribute, into a separate relation, which is the solution I advocate. So I think that you should typically, okay, BVZ's advice, put multivalued attributes into a separate relation. It's just easier that way. For one thing, it reduces the number of nulls. Another thing it does is it just makes it easier on your queries, because if you're looking to see whether a phone number, let's say you want to know whether a phone number is associated with a certain branch, it's a lot easier to say something like is phone number in select phone number from branch where branch number equals B3. I think it's easier to say that than to say is phone number equal to phone 1 or phone number equal phone 2 or phone number equal phone 3, and you still have to say something about where the branch number is equal to B3. I just find this to be easier to express, and it gets worse if there's 5 or 6 columns with the same phone numbers. So I just find it easier to put multi-valued attributes into their own separate relations. So now you would have branch number and phone number like that, and your branch number, and in this particular relation, the only primary key is the combination of branch number and phone number. Okay, branch number by itself is not enough. So questions about that? Okay. So in first normal form, we've eliminated multi-valued attributes. So first normal form eliminates multi-valued attributes. Second normal form is going to eliminate partial dependencies. Okay, so if we have let's give an example. Easiest to give an example. So we might say that, let's say we have staff number and branch. Say we decide that staff number and branch number uniquely determine everything. So it determines the staff name, the salary, and let's say the branch address. We'll just keep it to that. Okay, so turns out that this is not, while this may be, this doesn't uniquely determine these attributes. So staff number uniquely determines staff name and salary, and branch number uniquely determines branch address. So we don't say this is not a full functional dependency. Okay, it is a partial dependency because we can take subsets of that left-hand side, and subsets of that left-hand side uniquely determine subsets of the right-hand side. So in fact, the top thing is what is called a partial dependency, and we want to eliminate that. The way we eliminate that is we'd create two new relations based on these two functional dependencies, full functional dependencies. So that is what second normal form is we want to remove all partial dependencies that are on the primary key. Okay, so we start and we identify the primary key, then we identify the functional dependencies, and if there's any partial dependencies on the primary key, we're going to remove them by moving the attributes in that functional dependency to a new relation. And we'll remove the right-hand side attributes from the original relation. So to illustrate, here's another sample relation. It's a client rental relation. So basically, it's showing a lease. Okay, so this is lease information. And we can identify a number of functional dependencies here. So the client number and the property number uniquely determine the start and finish of the rent. So we're going to assume that no client rents the same property twice. We're going to assume that given a client and a property, that uniquely determines the starting rent and finish. Well, if we think about it, these two attributes also uniquely determine the client name, the property address, the rent, the owner number, and the owner name. But we don't include those attributes in this dependency, and the reason is because those attributes, like client name, can be determined by a subset of those attributes. So client number uniquely determines client name. It doesn't require the property number. And similarly, the property number uniquely determines the property address, the rent for that property, the owner number, and the owner name. So up here, we only list these two attributes on the right-hand side. So the primary key is client number and property number. Together, those two attributes uniquely determine every attribute in the tuple. But their combination is only required to uniquely determine rent start and rent finish. Individually, they uniquely determine the other attributes. Okay, then the owner number determines the owner name, and there are some alternate candidate keys as well. So the client number and the starting rental date will uniquely determine everything. Okay, so the client uniquely determines the client name. And then we said that a client can only rent one unit at a time. Therefore, knowing what the client is and what the rental start date is, we know all the other attributes as well. We know what property the client rented. Okay, similarly, if we have a property number and the date on which that lease started, we know all other attributes, or can determine all other attributes. Okay, and there's two other candidate keys. Okay, what are the two other candidate keys here? This is a bit like the booking relation. So the client number combined with what else will also uniquely be able to determine everything? How about rent finish? Not just the starting date, the finish date should also, if the starting date and a client uniquely determines all the information, then the client number and the finishing date also uniquely determines everything. Same thing with property number. If the property number and the starting rental date uniquely determines the lease, it must also be true that the property number and the finishing rent date uniquely determine it. So there's actually 5 keys, candidate keys for this particular relation. Okay, any of them could have been used as the primary key. Okay, but since we're going to use the client number and the property number as the primary key, we need to eliminate partial dependencies involving this particular functional dependency. And the two we have are client number determines client name, and property number determines all these other attributes. So what we do is we create two new relations, one that has client number, client name, the other that has property number with its attributes, and we have removed the right-hand side attributes from the old relation, which is rental. So rental is the old relation. Property owner and client are the two new relations. And we can reconstitute the original relation through joins on the client number and the property number. Okay. So basically, when we go to second normal form, what we're doing is, so to go from first normal form to second normal form, we move all attributes, not all, so we copy all attributes in a partial dependency on the primary key to a new relation. Okay, we remove from the original relation all right-hand side attributes. From the partial dependency, or from the dependency we moved. And the left-hand side, or the determinant attributes, which are the left-hand side attributes, remain in the original relation as the foreign key. Which I'm abbreviating as FK. So that's the partial dependency. Okay, so we do that for each partial dependency on the primary key. Okay. And we also need to ensure that any attributes in transitive dependencies move as well. So there was a transitive dependency so owner number determines owner name. We have to make sure that the owner name moves with the owner number, because that's part of a transitive dependency. Okay. Back here, technically speaking, we could have said that the property number only, that we wouldn't have to actually have this arrow here to owner name. So technically speaking, property number might be said to simply determine the property address, the rent, and the owner number, and then the owner number is what determines the owner name. So we have to make sure that transitive attributes follow us.